Okay, so welcome back. Now we are down to the business of actually writing algorithms to play games, and we are assuming that our game playing programs will do a finite amount of look ahead, and on the horizon they would apply the evaluation function, and then our task is to back up these values given to us by the evaluation function, decide what is the value of the root node or the value of that game tree or the game subtree, and based on that make a choice as to what move max should make essentially. So, we have studied the minimax backup rule. So, if you remember the minimax backup rule, it says that at the min level you take the smallest value from its children, because it is a minimizing node and it looks for the smallest value. At the max level you take the largest value from its children, because it is a max node and it wants to drive the game towards plus 1 or whatever it has been scaled to, plus large essentially. And we are also observed that we can do this in a bottom up fashion, and so this is how for this particular game tree we back up the values essentially. So, you can see that we have started from the bottom level, the first 5 is the smaller of the two values 21 and 5, 11 is smaller of 15 and 11 and so on. We have finished the min row and now we are moving to the max row. 11 is the maximum of 5 and 11, 9 is the maximum of 8 and 9, 12 is the maximum of 5 and 12 and so on. And in this fashion we are moving up the tree, and eventually we figure out that the minimax value of the game is 12 essentially. And therefore, max would make a move, would make the move which from where this value comes, and then wait for min's move as we have just discussed essentially. The minimax algorithm is the simplest algorithm that we can use for computing the minimax value, and here we have given a recursive version of the algorithm, and we can also write iterative versions. So, we know for example, that we can maintain an open list and keep adding to that. So, in the recursive version we do the following: we initialize max to minus large and subsequently we will look for higher values. Now, the base clause in recursion is that if it is a terminal node, and if it is a terminal node we simply return the value given to us by the evaluation function. If it is not a terminal node, then we do recursive calls. So, remember that for max we will look at each of the children one by one. So, recursively we will call the first child, and this is what is shown here. We initialize the value of that max node to minus infinity or minus large if we are implementing a real program, and then for each child c of n we start with the leftmost child. We recursively call minimax the same algorithm, compute the value of the child, and max chooses the maximum of the value that it had to start with and the value that is returned to it by the minimax algorithm, the recursive call to the minimax algorithm. Remember that we initialize max to minus infinity. So, the moment the first child gives a value, that becomes the value of the max, and as it proceeds looking at other children, it will possibly update its values to higher values essentially. If the recursive call was made at a min node, we initialize it to plus large or infinity, and then we look for lower values from there onwards, because min is always looking for a lower the lowest possible value from all its children essentially. Now, the minimax algorithm, it does a depth first traversal of the tree applying the minimax backup rule essentially. The minimax algorithm sweeps the entire tree, it traverses the entire tree in some sense blindly, simply applying the minimax rule essentially. But we want to look at situations where you may want to ignore some parts of the tree. So, this is the simplest kind of a situation, that if max has found a value of plus large from one of the children, then that is the best that max can do, it cannot do any better than that. So, there is no point in looking at the other children of max. So, we could prune those children and save time by not making recursive calls to those children. So, in this case Max has found a winning move and it does not need to explore any further, but we will see that this process can be extended to moves that are not winning moves essentially. So, it does not have to be plus large for such pruning to happen, it can happen with other values and this is what we will study now. Help us do this in a systematic way, we will adopt some nomenclature. So, we will adopt the following terminology and the corresponding observations with these modes. We will call max nodes as alpha nodes and they will store the value which we will call as alpha values. Remember that the algorithm Minimax that we just very quickly referred to is doing a depth first traversal of the game trees, sweeping from left to right, and it has partial values as it goes along and keeps updating them as it does more search. So, the partially computed values you will call as alpha values or even the fully computed values. So, max nodes will be called as alpha nodes and they will store alpha values, min nodes will be called beta nodes and they will store beta values. The alpha value is the value found so far for the alpha node. Remember that the algorithm is sweeping from left to right and it will be a lower bound on the value of the node. Why a lower bound? Because if it has got a value x from one child, left child let us say, then from any other child it would only accept a value which is higher than x essentially. So, any value it has found can only be increased for a max node and that is why it is a alpha value is a lower bound for that. It can only be revised upwards and it will reject any lower values offered by any of its children subsequently. So, in that sense we can think of the game tree as a kind of a supply chain mechanism where all the internal nodes are kind of traders in a sense, that an alpha node or a max node is looking at all the suppliers and saying give me the and it will take the maximum value from the suppliers, and the beta node or the min node is also doing the same except that it will choose the minimum values from its suppliers. So, once both of them have got one value, they can only look for better values in the case of max are higher values and in the case of min they are lower values. So, the situation for min is similar, beta value is the value found so far for the beta node and it is an upper bound on the value of the node, because it will not going to go above that, it will only look for values which are smaller and it will reject any values which are higher subsequently. So, let us look at this simple game again, tic tac toe, the same example that we saw a short while ago, and max is considering making this move which is putting a cross on the corner square and it is doing 2 ply look ahead. So, it looks at each of the children one by one, remember this is depth first search which is happening. So, first it looks at the first child and evaluates the first child, the value of the first child is 1 and you can do this as a small exercise, that max has 6 rows, columns or diagonals available and min has only 5. So, it evaluates to 1. So, at this point you can say that the beta node which is A has got a value of 1. So, beta node A is only going to look for values which are smaller than 1. So, the search continues, it looks at the second node, it turns out that the second node is, as you can see, symmetric. So, it is not surprising that the value of that node is 0. The third node has a value 1, the fourth node has a value 0 and the fifth node, as we have seen earlier, was the value -1, and by the time all the children of this beta node are visited, the value of beta has become -1. What does this mean? That this is a value that beta will send to its parent alpha node, and as you can see here, it means that alpha is going to be greater than or equal to -1. Why is that? Beta, the first beta child which is A, has given it a value of -1, beta this child is fully solved and we know its value exactly, and it is offering a value of -1 to the root node, which is the max node. So, max has got -1 from this beta child, and so it is only going to look for values which are higher than -1. So, max continues its search in that first fashion. It looks at the second possibility, which is to place a cross on a side and applies the and generates the first child of that node, which is, let us say that min is playing a knot in the corner, and as you can see the value of that node is -1. So, which means that the value of this beta node B is going to be less than or equal to -1. Now, you compare these two values. The root node has a value which says I want to be greater than or equal to -1, and the node B, which has not yet been fully explored, only one child of B has been seen, but we know at this point that beta is going to be less than or equal to -1, because this value of -1 is an upper bound on this beta node and it is a lower bound on the alpha node. So, you can see that these two nodes, if you were to think of it, are not going to do any business, because beta is going to look for a value smaller than -1 and alpha has already got -1 from the first child and is looking for a higher value. So, at this point their cutoff occurs, and this cutoff is called as an alpha cutoff. Why is it called an alpha cutoff? An alpha cutoff is induced by an alpha value, and it is induced below a beta node, and it is induced when the beta node is no longer going to be promising for the alpha node, in the sense that the beta value that it is going to return or offer to alpha is going to be less than the value that alpha has already gone from its left child. So, these are the key features of cutoff that we can do. The first key feature is that it must already have a value from one child, and it evaluates the subsequent children in contrast to the value it has already gone. So, if the subsequent children are going to offer values which are worse, then we will simply tell them that you do not need to do any further processing of that particular node. No point looking at this search tree below that, and you can simply say that we are not going to do business. In other words, we have done a cutoff that node, and having done that, it will now proceed to the third node, which is the third move that max can make, which is to place a cross in the center. Now, in this case, you can see that even in the version in which there are symmetric, we have kind of removed symmetries. For the beta node, 4 children were cut off, because each node has 5 successors, just like the first beta node had 5 successors, the second beta node also has 5 successors, and 4 of them have been cut off. But imagine that instead of doing 2-ply search, we were doing 8-ply search, then the subtrees below all those 4 successors would have been cut off. So, pruning can sometimes be quite drastic, which is of course good for the program will terminate faster. So, we can do an influence analysis, and this is due to Julia Pearl from his book called Heuristics, where he describes this influence analysis of game playing. And at any given point, you are exploring a node which we will call as J, and you are in the process of exploring that node, which means you have got some values from the left children, which is called alpha 4, which the value that it has got so far is alpha 4, and it is looking at other children below that. And the question we want to ask is, till when should we continue exploring this node J, and by that we mean looking at making recursive calls to the children of J and getting their values and seeing if you are getting a better value. Okay, so, this is where my program was trying to get into. So, let us say this is a node J and it has a value of alpha 4. Now, if you look at this tree, what does this tree have? This tree has a string of partially evaluated nodes. Each of these nodes has been only partially evaluated. So, for example, this beta 2 would have certain other children that would be evaluated, this alpha 3 would have certain children that have been evaluated, they are yet to be done essentially. So, each of them is partially evaluated and we are focusing currently on this node j and we are trying to see whether to look at the other children of j essentially. Now, when will j influence the root node? You can see that because its immediate parent is beta 3, only if the value alpha 4 becomes less than beta 3, which is what I have written here, will it propagate its value upwards towards the root. But not only it should be less than beta 3, it should be less than beta 2 as well, because that is also a beta node sitting there. It should be less than beta 1 as well, because that is another beta node sitting as an ancestor of this particular node. So, as depicted here, this value must be less than all the values of beta 3, beta 2, beta 1 and so on. Likewise, if it is to go past its max ancestors, it must provide them a better value essentially. So, which means for example, for alpha 3, alpha 4 must be better than alpha 3 and better means higher than in this case. Likewise, for alpha 2 and likewise for alpha 1. So, essentially we can say that we can propagate a beta bound which is the smallest of all the beta values, and only as long as alpha 4 or the value of this node j is smaller than this beta, should you continue to investigate below node j. Likewise, we can propagate a value alpha which is max of alpha 1, all the ancestors essentially, and only if the value is higher than this alpha, we should propagate, we should continue to explore this node j. So, in some sense this node j operates within a window where the upper bound is beta and the lower bound is this alpha, and only as long as the value that it is getting from its children is in this range, should you continue investigating the children, otherwise you should simply stop essentially, and that then a cutoff would happen. So, there are two kinds of cutoffs. The alpha cutoff that we saw earlier in the case of tic-tac-toe game is induced by an alpha bound from a max ancestor, and the alpha cutoff happens below a beta node essentially. So, if you situation is something like this, that you are exploring a beta node and this is the node j that you are exploring at this moment, and you have looked at some children alpha 1, alpha 2 and you are looking at other children so on. The beta value that is going to be computed is going to be the smallest of the values of its children that it is exploring, and the alpha is some ancestor, max ancestor, which is on the path to the root. It could be the root or it could be some other node on the root, and for every such max ancestor, or alpha is the maximum of the values as we discussed in the previous this thing, alpha is max of these values. So, only as long as this beta is going to be larger than alpha, only if as long as this beta promises a better value than alpha, and better value for alpha means larger, will search proceed. The moment beta becomes less than or equal to alpha, we can do an alpha cutoff below this beta node, which means we can stop investigating this beta node and do not make recursive calls to any further children. The beta cutoff is similar. The beta cutoff is induced by a beta bound from a min ancestor, and it happens below an alpha node essentially. In a very similar analysis, the alpha value is going to be the maximum of all the values of its children beta 1, beta 2 and so on, and there is a beta bound sitting on the top. So, alpha value must be less than that beta value for it to have influence on the root. The moment that alpha becomes greater than beta or equal to beta, or in other words when beta is less than or equal to alpha, beta cutoff occurs. So, you will notice that the cutoff condition is the same for both alpha and beta, that the difference is that in alpha cutoff beta is the value being computed, and in alpha in beta cutoff alpha is the value being computed. In alpha cutoff beta is the value being computed, and in beta cutoff alpha is the value being computed, and the other one comes as a bound essentially. But remember that this is basically saying that the window is closed essentially. So, when we are looking at an alpha node here, for example, it is trying to increase the lower bound, and when you look at the beta node here, it is trying to decrease the lower bound. In either case, if this goes beyond the other bound, then we can stop searching essentially, and that is basically the idea behind alpha cutoffs and beta cutoffs. So, here is a algorithm, alpha beta algorithm, which we will quickly see. So, when we wrote Minimax, we simply gave a board position n as an input to the algorithm, but when we write the alpha beta algorithm, we give it two bounds, the alpha bound and the beta bound. So, the initialization of alpha is minus large and initialization of beta is plus large. So, if you go back to the window analogy that I just spoke of, it amounts to saying that the window is completely open, beta is at the topmost point and alpha is at the bottommost point, which is amounts to saying that the minimax value of the game could be anything within these two ranges. The rest of the algorithm is similar to Minimax in the sense that we have written a recursive version here. You can also write an iterative version in which you store nodes into open and maintain open as a stack and do all that kind of stuff. So, as before, if n is a terminal node, we return if n is a terminal node, we return the value n, that the value eval n, which is returned by the evaluation function. And if you remember in the Minimax algorithm, we had initialized alpha and beta to minus infinity and plus infinity respectively, because alpha could only become better than minus infinity and beta could only become better than plus infinity. But in the alpha beta algorithm, we are propagating these bounds. So, as search proceeds, we have seen that this window becomes smaller and smaller as we go from left to right, and these are the bounds that are propagated to every recursive call that we are making. So, we do not need to initialize at minus infinity and plus infinity here, we can directly work with the bounds that are propagated. So, as before, if n is a max node, then you start looking at a child C one by one, first, second, third and so on, and for each child you make a recursive call to alpha beta again, and for each child the value that you want to compute is the maximum of what it had got earlier. So, remember that this is the alpha value that you had got to start with when the call was made, and you are simply trying to see if you can get a better value than this. So, for each child we try to raise the value of alpha if we can find a better value of alpha. If at any point alpha becomes greater than beta, which means this window is closing, then we simply return saying that we can't give you a better value, just take the value beta that you sent to us as a bound essentially. So, that is a beta cutoff which is happening, and it is happening below a max node essentially. So, this is a beta cutoff. The situation for min is similar, that min has got also the same window beta and alpha, and min is looking for a lower value of beta essentially. So, when you make the recursive call to the child of min, you choose the smaller of what that call returns and what you already have, and if at some point beta has gone below alpha, which means again alpha is greater than or equal to beta, then you do an alpha cutoff. So, this is a algorithm alpha beta. It is probably the most popular algorithm that is used in game playing, and simply because it is so easy to implement and it performs much better than Minimax. Minimax just does brute force search over the entire tree, whereas alpha beta, it is also called the alpha beta pruning algorithm, can prune large portions of the tree, and as we will see, the amount of pruning it does depends upon the order in which moves are generated, and we will come back to that in the next session. But let us just look at an example of alpha beta algorithm. So, it also does Minimax like search, which means it searches in a depth first fashion left to right, but unlike Minimax, it may not explore certain subtrees essentially, and these happen when either the alpha cutoff appears or the beta cutoff appears. So, let us look at a couple of small examples to understand this. So, here is a small example that we had seen earlier, and you can see that this is happening in a depth first fashion. First we explore the leftmost subtree, then this subtree, then we get a value for this, and then we do the rightmost part and so on. Minimax would have explored the entire tree in the depth first fashion, whereas alpha beta in this small example has not looked at some nodes. So, what are these nodes? An alpha cutoff has appeared below the beta node 5, whose value is 5, and you can see that this has happened because this value 5 that. So, this is going to be less than or equal to 5, and this alpha has said it is going to be greater than or equal to 12, and alpha is not going to be interested in this beta node. So, it simply says stop exploring below any further, and this cutoff occurs below the beta node. Yeah, thank you. It should not be 12, it should be 9, because 9 is the value that is coming from here. This 12 value is actually only coming from this side essentially, but that has not yet been done. So, when this part of the subtree is explored, we know that this value is 12, and when beta starts looking below this thing. So, remember that this is a beta node. So, this is going to be less than or equal to 12, and this beta node has evaluated to 13, and so this alpha says I am going to be greater than or equal to 13, and again the beta node says that there is no need to proceed any further. I am looking for a value less than or 12, and you are giving something which is 13 or more. So, no point in progressing further. Observe that the subtree below that has actually a value which is 7, but this 7 is not going to influence this beta node, because max is sitting in between, and between 7 and 13 max will choose 13, and therefore, between 13 and 12 min has already chosen 12 and says that I am not interested in a value greater than 13. Let us look at a slightly bigger example in which there are more cutoffs. So, here is a larger tree, it has got 36 nodes, and you can see, and this is the final tree that I have drawn, and I would encourage you to do this exercise yourself, and in particular observe that in the nodes that have not been visited by alpha beta, which are these shaded nodes here, if you were to put in any value, it would not change the minimax value of the entire game tree. So, just to do a quick study of what is the cutoff happening here, you can see that from the leftmost side we get 12 here, because it is a min node, and we get 30 here because it is a min node, and between 30 and 12 max would choose 30, and therefore, this would be less than or equal to 30. It is getting one value from here which is less than or equal to 30. Now, when you go to the second subchild of this min node, you are getting a value of 40 from here, and this says that I am going to be greater than or equal to 40, and therefore, min says just you can cut that off essentially. Then min goes to the third child and it is getting a value of 70 and 25 here. So, this will be 25 and this says I am going to be greater than or equal to 25. So, this says this I am going to be greater than or equal to 25. So, which means min is still interested, because for example, if it was 26 or 27 or 28, min would still prefer it to 30. So, the search continues, and when we find the first value of 20 for a min child, this is saying I am going to be less than or equal to 20, but max is its parent is getting a value of 25. So, it says do this cutoff. So, this is an alpha cutoff which has happened. In a similar fashion, by the time this has gone up, this value of 25 would have gone here and it would have gone here, and so this would be greater than or equal to 25. And cutoffs can be very deep, in the sense then when the algorithm is exploring this node 17 here, and it can see that this is going to be less than or equal to 17, or the beta value is actually an upper bound, but so I have just written less than or equal to 17. Then the fact that its max ancestor is 25 influences the cutoff at the very deep level. So, even without knowing the value of its parent, a cutoff can be influenced by any ancestor, and this is what we had studied earlier. So, if you go through this whole exercise, you will see that there are some more cutoffs which are happening here. So, this is an alpha cutoff and this is a beta cutoff, because beta is getting some value. So, what is that value? Let us see, this is 25 from here and this is 60 from here, sorry, this is 57 from here. So, this would choose 57. So, this is going to be less than or equal to 57. This one is going to be less than or equal to, this is less than or equal to 17, and the other one is going to be less than or equal to 15. So, we are not even interested here, and at most this can be 17 essentially, and because this is 17. So, this 57 has gone down to 17, and again the root is interested in 25, and therefore, this will be an alpha cutoff below that. Okay. So, this is basically our first look at the alpha beta algorithm. It does pruning on the search tree. We will come back to this in the next session. We will maybe take another example. Then we will look for an algorithm which is better than alpha beta, in the sense that alpha beta has the same property, that it is like the Minimax algorithm searching the tree in a predetermined fashion from left to right. We would be interested in looking at an algorithm which is the best first version, which has a sense of direction, which does not necessarily explore the tree from left to right. We will also see that with a couple of examples of alpha beta, that given certain order of nodes, and by order of nodes we mean the order in which the tree is generated, alpha beta may do more or less cutoff. So, it would be dependent, the alpha beta pruning would be dependent on the order in which the children are generated, but the best first version that we will see would be independent of that. So, for any order, the best first search would do the same pruning, and that is the next algorithm that we will see. So, see you in the next session.